Hi everyone, welcome back to Food for Thought Physics. In our last video, we looked at weight, or the force of gravity on objects, and we saw that near the surface of the Earth, gravity is going to act on objects with a force, which we're going to call F sub g, equals m times g, the mass times this gravitational acceleration constant, which near the surface of the Earth is going to be approximately 9.8 meters per second squared. And we're going to include this negative symbol here to indicate that this acceleration is downward as gravity pulls things down towards the ground. So now, consider a box that you say you throw onto a table somewhere, or you set onto a table. And we're going to draw a little table here. Now, you might know from experience that if you put a box on a table, the box is not just going to start falling downward suddenly. In most cases, it's going to sit on the table and not move. Since this box doesn't move, that means that the velocity is staying at a constant 0. If the velocity is constant, that implies that the acceleration of this box must be 0, as the velocity is not changing, it's staying constant at rest. Now, if the acceleration is 0, then we can use Newton's second law, F equals ma, and say that the force on this box must be the mass times this 0 acceleration, which is still always going to be 0. So the force on this object must also be 0. Now you might wonder, how is this possible? Because we see there's a force of mg acting downward on this box. And so we think about this and we realize, well, that means that there must be another force on this box, canceling this mg out somehow. That force is what we're going to call the normal force. The normal force is called the normal force because it acts normally, which means perpendicular. And I'm going to quickly label this here. Normal is, in this case, is going to equal perpendicular. So this force is going to act normal to the source of the force, in which this case is going to be this table right here that our box is resting on. And the table is actually going to be pushing upward on this box with this normal force here, which I'll draw in red. And I'm going to label this as F sub n for F normal. And this force is going to be equal to negative mg. So it's going to have the same magnitude as this force of gravity, except it's going to be negative of that. The vector points in the opposite direction, which means that this force is acting upward. With both of these forces added together, we see, well, mg plus this negative mg, that means that the net force on this box is now 0. And if the net force on this box is 0, then we see, well, the acceleration must also be 0 here, since the force equals mass times acceleration. And if this side is 0 and the mass is not 0, that means the acceleration must also be 0. So we can actually write this as a bijection. This is true in both directions, as long as the mass isn't 0. And so we see here this normal force is acting perpendicular to this table here, to the surface of the table here. It's acting upward while the table is going to be horizontal. Now, you also might know from experience that if you put a really heavy box on a table, and the table is made of, say, some thin wood, then the table is probably going to crack and split in the middle, and the box is going to fall through. Why might this happen? We see that the net force on this box is 0, so why would the table break? Well, if we remember Newton's third law, this third law states that if one object acts on another object with some force, then that object must also act on the first object with the same force, but in the opposite direction. In this case, we see that, well, this table here is pushing on this box with this F normal equals negative mg. That means that the box must also be pushing back on the table with a opposite force, which is going to be equal to just mg, positive mg, which is going to, in this case, since g is negative, it's just going to mean it acts downward. And if this mg here, the force that the box is exerting on the table is too large at any given point, then the table's wood, or whatever it's made of, might give away and it might split, which will break the table. And if the table breaks, then we see, well, there's no more solid surface here pushing upward on the box, so this normal force disappears. When the normal force disappears, we see, well, the box is just going to fall, because the only force now is just this mg right here. Now, one important thing to note is that whenever you do physics, you need to keep track of which forces act on which objects, and drawing a diagram like this helps. This is actually called a free body diagram. A free body diagram being just when you draw out a diagram. This is going to be a free body diagram. A free body diagram is just when you draw a diagram of all the objects you want to look at, and also draw all these forces as vectors, and keeping track of which forces act on what object. And here's why this is important. We see, well, there appear to be 2 mg's here, and acting downward, and there's only 1 negative mg acting upward. So, doesn't it seem like there's more force going down? Well, no, because this force right here is the box pushing on the table. This doesn't actually accelerate the box in any way. The accelerations on the box are just this mg and this mg. The mass pushing down on the table is only going to try to accelerate the table. And actually, we see in this case, if the mass is pushing the table downward, and the table, as long as it doesn't break and it doesn't split here, well, the table must not be accelerating either, since we don't see tables just randomly fall through the ground. Which means that there also must be some normal force from the legs of the table acting up, where the ground is actually pushing up on the table. And assuming we have some 4 legs, then we can estimate each of these as just being negative mg over 4 and negative mg over 4, assuming there are 2 other legs that are not drawn here. And similarly, as we see here, that means that all of these legs must also be pushing down on the ground. Well, actually, this force is actually going to be a little bit greater than this. The table is going to have some mass, and this is going to be something like, if we have a table with a mass, we might add, say, the mass of the table, which we're going to just call T right now. So the mass of the table times G over 4, and maybe over here too, mass of the table times G over 4. And so there are, of course, more forces. The table is pushing down on the ground as well, and there might be some forces at these joints here. But the point is, by drawing out a diagram like this, we can kind of see, well, which forces are acting where and on what objects. And we can figure out a lot of stuff from this free body diagram here.